first the different ways that we'll be representing numbers in this class. So those are decimal, binary, and hexadecimal. All of them have their unique strengths and purposes, which we'll go over. And we'll also look at how to convert between the three of them. And then we're going to talk about how to deal with, we got someone else. Then we're going to talk about how to look at negative numbers and how we process negative numbers with 2's complement and bias. So if any of those terms are unfamiliar, don't worry, we're going to go over all of it. And then I've selected a handful of discussion problems to look at. Everyone able to find the discussion sheet okay? Does everyone have access? Okay, cool. I'm seeing some thumbs up. Excellent. Cool. Okay, so yeah, let's look at the three principal methods of number representation in this class. So first we have decimal, which you all are maybe familiar with, the decimal system. This is base 10, what we are used to writing numbers in. And the reason we're going to talk about it here is because this gives us a familiar starting point for using other bases like base 2 in binary and base 16 when we get to hex. So if I write a number in decimal, right, say right 365, I can also express this in terms of powers of 10, right? It can write 3 times 100 plus 6 times 10 plus 5 times 1. And we sort of see this pattern emerging where I have some digit, so some number less than 10, 0 through 9, times some power of 2. And the total number is expressed as the sum of digits times power of 10. So I can also write this as 3 times 10 squared plus 6 times 10 plus 5 times 10 to the 0, 10 to the 1. And here, 10 is referred to as our base or radix. So does anyone have any questions on this expansion of decimal numbers? All right, cool. So the reason I show you what might seem like a simple example is to then get into how we expand binary numbers. So a binary number is a sequence of 1s and 0s. And this is how our computer, or the computer, processes information. Specifically, in this case, numbers, but as we'll see in this class, that can extend to letters, to instructions, to programs themselves. All sorts of things can be represented in binary bits. So for example, if I have the number 0, 1, 1, 0, and I'm going to prefix this with a 0b, this is a convention that you'll see a lot in this class to specify the system, the representation system, or the base that we're working with, b being binary. I can break this down in the same way that I did my decimal expansion. Here we're working base 2. So what I can do is I can write this as a similar sum of 0 times 2 to the 3rd plus 1 times 2 squared plus 1 times 2 plus 1, or 0 times 2 to the 0. to the 1, which if I add up, I get 6. So that's a very simple example of converting to binary, but this process of expanding things out and using the base is going to be consistent through hex and through any other arbitrary radix that you're given. And sort of as a motivation for why we use 0 and 1. So when you think about what happens under the surface of your computer and looking at the very transistors and such that go into the processor and everything under the surface. Yeah, it's someone, Antoine says, is it about the voltage? So that's exactly right. We process signals and information is processed in the computer as a series of high and low signals of voltage or sort of, yeah, well, in high and low voltage signals. And because there are sort of very discrete steps between like a low voltage and a high voltage, we use a 0 and 1 to indicate an off state and an on state. So if you go on to take classes like EX151 or some upper div EE classes, you go into more detail here. It's not super important for this class, but I just like knowing sort of why we're doing this. What's the point? What's the motivation? So now we're going to talk quickly about hexadecimal, which is base 16, and the purpose of representing something in hexadecimal is to provide a compact method of representing large binary numbers. So in the case here of 6, this is only 4 bits. So it's pretty straightforward to write out and process by hand. But as you'll see in this class, when we're dealing with 32 or 64-bit values, it's a lot more inconvenient to write all that out by hand and convert back and forth using just the powers of 2. So we introduce hexadecimal to represent large numbers in a compact format. So I'm going to give you an example here. I use the prefix x, 0x, to indicate that we're working in hex. And here, oh, we're seeing some answers in the chat, cool. We have 2 base 16 values. So to extend our traditional digit system to base 16, we take the digits 0 through 9 with their original familiar meanings. And to represent the values 10 through 15, we introduce A through F. So something that as you work through homeworks and discussion worksheets and exam studying that you want to get familiar with is thinking about A as 10, B as 11, so on through F as 15, and what these values look like in binary, right? So 15, it's all ones, and then we'll have 11, which will be 8, 2, 1. So these are, you want to get used to converting quickly between these and memorizing them. No worries if it seems a little overwhelming now. But to convert from hex to decimal, we can sort of use the same expansion that we used above. Remembering this time that our base is 16. So 0x1a can also be thought of as 1 times 16 plus 10, which is equal to 26. Now, as it's mentioned in the chat, we have an alternative representation for this value in binary, and hex and binary play very nicely together. So 1 in hex, or A, right, each of these are at most 15. There are 16 possible values that a hex place can take on, a hexadecimal place, from 0 to 15. So similarly, 4 bits can take on place from 0 to 15, because 0, 0, 0, 0 is 0 in decimal, and 0, and then 1, 1, 1, 1 is 15. So a very convenient property of hex, and as I mentioned, the reason it allows us to give a compact representation of binary numbers is that each hex value is directly convertible to 4 bits. So when we're converting from hex to binary, we can convert, instead of converting this entire large number, we can go one place at a time. So I say, so looking at the chat, right, as we can see, 1 can be represented as 0B, 3 zeros, and a 1. And A, which is 10, is 8 plus 2. So that's a 1 in the place that corresponds to 2 to the third, a 0, 1, 0. Something else that this allows for is converting from binary to hex very quickly. We only have to look at 4 bits at a time. So if I wanted to go backwards here, I only have to convert this chunk of 4 bits to a hex value, and then the next chunk to a hex value. And if the number was larger, go so on and so on. So these are the basic schemes of number representation that we'll be looking at in this class. Anyone have any questions? Any questions at all? Why do we learn hex? Great question. Seems kind of confusing and scary to look at least that was my reaction. So hex is a way of taking some very large values in binary and representing them in a bit more readable format. So for some of these toy examples that we're looking at here, that might not be as clear, but later on in this course, once we get to things like machine code, so that's taking, basically going from your C code to assembly language down to bits that are fed to the CPU, you're looking at values that are up to 32 bits long. And it's very inconvenient to write out 32 bits. And it's very error prone, or it's very easy to be error prone when you're writing out 32 ones and zeros and trying to get them to match exactly to some like instruction code and other things that you'll learn about in a couple of weeks. So we write those very compactly as hexadecimal values. It's much easier to print and much more convenient to work with as a student, especially when you're writing things out by hand or debugging in RISC-V or things like that. Anything here that sounds unfamiliar, don't worry about it. We're going to get to it in a couple of weeks. But for now, you can just think that hex is a really convenient way to write large binary numbers in a compact format. Cool. So now we're going to look at dealing with negatives. So as we've been looking at these binary values, right? If I was to write out, again, just some arbitrary value in binary, right? So this is 10, as we saw before. I can think about using more and more bits to get larger and larger positive numbers. But this system isn't really all that convenient for representing negative numbers right now. There's a concept in this class that you'll probably hear about a lot, and something that when I took it with Dan Garcia, he liked to say, and that was that there's no free lunch here, which means that to represent more information, you need to use additional bits. So in the case of negative numbers, our binary representation as is isn't super conducive to representing negative numbers. Ain't no free lunch. Exactly. Yes, Dan. Dan's the man. He's awesome. So we are going to use some other bits to represent information about negative numbers, particularly the sign and whether or not we're looking at a positive value or a negative one. So there are a couple ways that this is done, and a few that you'll be introduced to in lecture and homeworks. The first is something called sign and magnitude. And what this is exactly what it sounds like. We have a bit for the sign and a bit for, or then the rest of the number is used for magnitude. So for example, let's say I want to represent -10. I could do something like 0, B, I'm in binary here. I have a 1, and then 10. And when we're working under this convention, we just accept that the first bit of any value is going to be our sign. So if it's a 0, it's positive. If a 1, it's negative. So this sounds pretty good. Does anyone see any potential issues with this representation?
Isn't there like 2 zeros or something?
Yeah,
Negative
yeah.
and positive.
Right. So there ain't no free lunch in this world, but we also don't like to waste things, right? To be inefficient. And when we have 2 zeros, not only can this be confusing in some calculations, but it's also not the most efficient use of all of this bit real estate that we have. So we introduce this concept of 1's complement, 2's complement, which deal with the idea of sort of flipping the bits to get rid of this 2 zeros problem. So I mentioned 1's complement because it's something else you might see thrown around, but we're not going to go over it because 1's complement was introduced, and then later on, the idea of 2's complement was introduced, which was a much improved version of the system and the one that you are going to deal with most commonly in this class. So it's here because you should know it's something that exists, but in the interest of time, we're just going to focus on 2's complement, which allows us to represent negative numbers with only a single 0. So how does 2's complement work? Well, in the most mechanical sense, if I'm given a number, just a regular binary number, so no negatives, something we call an unsigned binary number, unsigned because there's no positive or negative sign. So in this case, again, 10, in order to generate a representation of -10, what I want to do here is flip all of the bits and then add 1. So this becomes +1. And this resulting value is my 2's complement representation of -10. So this might seem like sort of a random calculation that's relatively unmotivated. As you work with it, and as lecture elaborates on it, it will, I guess, make a little more sense as to why we do this and some of the problems it solves. In the interest of time, I'm going to just show the basic mechanics, and then we're going to move on to the worksheet because I want to take a look at some of the problems there. But to come up with a 2's complement number, we flip the bits and add 1. And then to convert from 2's complement, the first bit's supposed to be negative. Oh, yes, it is. Good point. So flip the bits and add. Huh. What did I do wrong there? Yeah, so that first bit should be negative. Yeah, wait 1 sec. I'm gonna check on that real quick. Sorry about that. Sorry about that. Oh, yeah, okay, that's right. I see. Okay, so what I forgot were the preceding bits here, which would be zeros. So then when you flip the bits, because you have all these implicit preceding zeros, you get 1, 1, 1, 1, which, yeah, so yeah, just like Clint said in the chat, you have a implicit preceding 0, which is flipped to be a 1. So then the final representation is 0b. All right. So with that, to convert from binary representation of 2's complement to a decimal, back to a decimal value, what we do, a very convenient way of doing this, is taking the first one of the preceding train of implicit ones and multiplying that, turning that to a negative 1. So we do negative 1 times, in this case, 2 to the 4th plus 0 times 2 to the 3rd plus 1 times 2 to the 2nd plus 1 times 2 to the 1st plus 0 times 2 to the 0. And this gives us 16 plus 4 plus 2 is negative 10. So the other method that we use sometimes to represent negative numbers is the bias method, in which we define a bias that is applied to our unsigned binary representations. So let's say I set a bias of -3. In that case, 10 is interpreted as 7, because what we do is convert this to 10 and then apply the bias, it's -3, and end up with 7. So I mentioned that because that is another term that will be thrown around on the worksheet. So any questions on negative numbers? Oops. On 2's complement, bias notation, number representation in general before we move into the worksheet? 7 is so the question is 7 the actual number or the biased number? So if I understand your question correctly, I want to say both because the actual number is the biased number. So the bias is, so the unsigned value, the original value of these bits just interpreted as an unsigned binary value would be 10. But when we add a bias, it's saying that all values, like all unsigned representations, now are seen as that representation plus minus the bias. So in whatever setting this number is being used, so whatever application or anything, 1010 is treated as 7 because we have a bias of -3. Cool. All right, let's jump into the worksheet. So I have highlighted a couple questions. We're gonna skip over the pre-check questions because these are more conceptual check-in questions. So highly recommend you go through these on your own, but for the purpose of discussion, we're gonna take a look at starting with 2A. Just do, we're gonna do let's do 1 and 5 on 2A to convert the numbers from their, actually 1, 5, and 7 on 2A, where you're gonna be converting this binary, decimal, and hex number into the remaining two radices. How are we doing as a group? Anyone else? Do people want more time or do we want to go over them now? Just got done? Sweet. Ready? All right. Antoine, are you all right if we start to go over them now? Cool. All right, so does anybody want to share their approach? You don't have to even give an answer, but just how you thought about starting part A, number 1, converting this binary number to decimal and hex?
Yeah, so basically you just take each so I went from right to left and I
Okay.
took like 1 times 2 to the 0 and then just kept going
Mm-hmm.
on 1 times 2 to the 1
Mm-hmm.
and etc. And ended up getting 147.
Yeah, definitely. That's right.
And then
So,
I just saw this from the lecture kind of thing
mhm.
because it says put it in both other number like bases, right? So we're gonna do
Yep.
hex, I'm
Mm-hmm.
guessing. So then what I did was I just grouped like the bits into
Yeah.
4 bits
Yep.
because then you have 16.
Mm-hmm.
So then 0011 is 3,
Mm-hmm.
and that can be represented in hex. So then you're gonna get OX, and then 1001. I thought of 1000, which is 8,
Mm-hmm.
right? And then so you just add 1 to that, you get 9. So I
Great.
got 9 and 3.
Yeah. Great. Yeah. So that's exactly right. Using the decimal or the binary expansion method that we saw to convert it to decimal, and then taking each individual set of 4 bits. There we go. Each set of 4 bits to interpret as a hex value and convert this binary value to hex. Yeah, that is exactly correct. And that's a great approach to take. Thank you for sharing. Anybody want to give number 5 a shot?
So what I did was eyeballing that 39 was 32 plus 8 plus 1.
Great.
32 plus 4 plus 2 plus 1.
Yep.
And I tried to use the method he used in class, which is trying dividing the number by 2.
Okay.
And that didn't work out for me. Can you go through that process?
Yeah, sure. So when you say dividing the number by 2, is that
Like using the remainder as
Oh.
yeah.
Okay. I'm not sure how familiar I am with that method. I'm familiar with another similar method that might be the same thing that I can show you, and then let me know if it's
Okay.
different.
Sure.
Yeah, I don't want to go through something that I'm not totally sure what it is. But this might be similar because what you mentioned first about looking at recognizing that we have first 32 as like our largest power of 2, and then we want to look at the powers of 2 in the remainder. Yeah, I see in the chat. Otherwise, you can use powers of 2 like 63, 64 minus. Oh, yeah, okay. I see. Yeah, so for taking the like largest power of 2 out of this value in decimal, what I've done in the past was to say, okay, we have 39 minus 32. So that'll be a 1 in the 2 to the 5 place. And then what's left is 7. So there's no 16 in 7. So if I was to write the powers above, I would say 5, 4, 3, 2, 1, 0. So there's no 16. There's no 8. There is 4. So I'll give that a 1. And I'm left with 3. There is 2. 3 minus 2 is 1. There is 2 to the 0. And then we're left with 0. Does that look familiar to what was done in class, or is it different?
Yeah, it's not exactly the same, but I think the principle are the same.
Okay, cool. But yeah, so in this case, we've taken the highest powers of 2 and subtracted them. You can think of these as sort of egg crates that you're filling in, depending on whether or not there's a large enough value to fit. But yeah, so then do you have any thoughts for converting this to hex if I give you this number in binary?
Yeah, it's essentially just the reverse process of what we did with number 1, right?
Yeah, exactly.
So 0, 1, 1, 1 would be 3 in hexadecimal.
Yep.
And 0, 0, 1, 0 would be 2 for hexadecimal, right?
Yeah.
So it'll be 0x29.
X2. Oh, yeah. Oops. 3 plus.
Wait, that one's 7, right?
7. Yeah. 7.
Oh, 7. I'm sorry.
Cool. No worries. All good. Great. So then for part 7, we're gonna just move to part B for the remainder of the discussion. But for 7, you do something very similar, although this time you're starting from hex. So converting to binary, you just want to take each hex value and interpret it as 4 bits. And then decimal, you can either expand the hex or expand the binary. The expanding the hex will be a little less involved. The binary will just be a large sum. So we have about 5 minutes left before we as to
Can you spell it in the chat?
Yeah, good idea. Okay, so why don't we just talk about part B as a group, if that's all right with everyone, for the remaining, yes, France, the French Revolution. They were like, base 10, base 12. So people jokingly were throwing out 11. So cool. Anyone want to give a suggestion on where we should start with part B, converting from hex to binary?
We just go one digit at a time.
Yeah, exactly. Exactly. So we have 4 hexadecimal places, which means we're going to have 4 segments of 4 bits. So 16 total bits, and each section of 4 corresponds to one of the hex places. So anyone want to tell me what D is first in decimal, and then we can think about it in hex? Seeing in the chat, 13. Anyone want to agree or disagree? Seeing an agreement? Yes. Yeah, so that's 13, right? So does anyone have any ideas to how we want to represent that in binary? 13, 4 bits.
So I know 1100 is 12, so then you just do 1101.
Yeah, great. Yep, and then 3 is our next value. Anyone want to put out? You can just toss an answer in the chat too. Either way. Yes. 0, 0, 1, 1. We have A, which is 1, 0, 0. So that's 1, 0, 1, 0, 10. That is correct. And then D again. All right. So that's going to be about it for today's discussion. If anyone has additional questions, I'll stick around until this meeting room closes or however it works. But I'll stick around and answer any additional general questions. But that's going to be it for problems. And I'm going to stop the recording.